Hi friend, you are welcome back to my channel, and in today's video lesson we shall be talking about another important topic in physics, which is calorimetry. So without wasting your time guys, we'll be getting started now. Now first thing first you need to know is what they call the different formulas in calorimetry. Now to get what is called the quantity of heat or simply heat, and this is symbolized by either Q or H. So all these formulas that are here, in place of H, you can put Q, okay? Now that's for that. To get the quantity of heat, first thing first, the unit for quantity of heat or heat is simply Joule. You can use different diverse formula to get your quantity of heat. You can say heat is equals to m small c times change in temperature, or heat is equals to big C times change in temperature, or heat is equals to m times big L. Now each of these big C, small c, big L, they have their meaning, which we see below. And we know that m is mass, change in theta is what? Change in temperature. Okay? Now these are the formulas you can use to get quantity of heat. You can also make use of this formula. Heat is equals to power times time. Okay? Or heat is equals to current times voltage or potential difference times time, or heat is equals to current squared times resistance times time, or heat is equals to voltage, or you say potential difference squared over resistance, whatever you get, times time. So we'll be understanding how all this came about as we progress. Okay, so now we know that that is for quantity of heat. Like I said, all this H can be replaced with what? Q, because heat has two symbols, either Q or H. Now moving on to the next, we have what is called specific heat capacity. This is denoted by small c, and the unit for this is joule per kilogram per Kelvin, or joule per kilogram per degree Celsius. Is the same thing. Okay, Celsius or Kelvin is the same thing. Now we are talking about the small c, like the one we saw here. How do we get the small c? Let's say in a question we were asked to find the specific heat capacity, that is the small c, of a given substance. What is the formula to use? From this formula of heat, if we make small c subject, we'll get this as the formula for specific heat capacity. And what is it? Small c is equals to H or Q over mass times delta theta, that is change in temperature. Okay, this is the formula we can use to get our small c, specific heat capacity, and this is the unit. Now if you were asked to find what is called heat capacity or thermal capacity, given as big C, the unit that you should know for this guy is joule per Kelvin. Now mind you, there is no per kilogram in this, because this is talking about the amount of heat the whole body possesses, while this is talking about the amount of heat a unit mass of that body possesses. The whole body, a unit mass. So that's why this one is called specific, because it's talking about the amount of heat that a unit mass of the substance need to increase the temperature by 1 degree Kelvin or 1 degree Celsius. I hope that is clear. Why this is the amount of heat, joules, required to increase the temperature of the whole body by 1 Kelvin, or you say 1 degree Celsius. Mind you, like I said, for this, the formula, the unit for this can also be joule per degree Celsius. I hope that is clear. So if we're asked to find big C, thermal capacity or heat capacity, what's the formula to use? Now from this second formula of heat, if you make C subject, you can say big C is equals to heat over change in temperature. It's quite different from this, right? Good. Now there is something called specific latent heat, and there are two types of specific latent heat. You have the specific latent heat of fusion, given as L subscript F, and you have the specific latent heat of vaporization, given as L subscript V. Now, for L subscript F, a simple gas, specific latent heat of vaporization. Now there's a formula you can use to find any of these. So I just pick their LL because the formula is the same for both. So we can say L is equals to quantity of heat over the mass. So the quantity of heat that was used up in the conversion from one state to another over the mass of the whole body will give you the specific latent heat. And the unit for this, okay, the unit for this is Joule per kg. Take note of this. That's the unit for specific latent heat. Now we go to what is called heat summation. Sometimes we need to add more than one heat to get the total quantity of heat. Let's say a body is changing its state from one state to another. It's not just one heat that was used up there. Many heat was used up. Now take for instance the example I cited here. I said in the conversion of water, okay? No, let's just say in the conversion of ice block at 0 degrees Celsius to steam at 100 degrees Celsius. Now ask yourself, what is the initial? Ice block. What is the final? Steam. You know that from ice block state to steam state, different things occur. Let me analyze it for you. Now, they say ice block at 0 degrees Celsius. Ice block at 0 degrees Celsius is in which state? Solid state. Now, before it converts itself to water in at 0 degrees Celsius, heat must be used up. And that heat is a hidden heat because that heat is not going to cause a change in temperature. Okay? Now, take note of something here. Specific heat causes change in temperature. Latent heat causes change in state. And whenever there is a change in temperature, there will be no change in state. And whenever there is a change in state, there will be no change in temperature. That's why we take note, when water is being converted from solid state to the liquid state, there is no change in temperature. That's why you now say the freezing point, or no, you say the melting point of water is what? 0 degrees Celsius. It's just one temperature that will occur there. During that conversion from solid to liquid state, we say 0 degrees Celsius. Why is there no change in temperature? Because the heat that is being used up is a latent heat, not a specific heat. Now, after it can be converted to water at 0 degrees Celsius, because that water will still be at 0 degrees Celsius. Let's say you now heat it up to 100. What occurs is that there is an increase in temperature. There is a change in temperature. Now, from 0 degrees Celsius, water at 0 degrees Celsius to water at 100 degrees Celsius. Was there a change in state? No. It was still liquid water, is it not? So whenever there is an increase in temperature, there is no change in state. Now, when that water is now at 100 degrees Celsius, so you are visualizing water at 100 degrees Celsius. Now, it will now be converted to what? Steam, and steam is a gas. So from liquid to gas, at that same 100 degrees Celsius, there is a heat used up. That heat is latent heat. And during that conversion from liquid to gas, there is no change in temperature. The temperature is constant, 100 degrees Celsius. What is only changing is what? State. So take note, the heat required to cause a change in state is called latent heat. The heat required to cause a change in temperature is called specific heat. I hope that is clear. So looking at this guy, the ice block was initially at 0 degrees Celsius. He wanted to change to water, that is from solid to liquid. The first heat that will be used up is what? A latent heat. See, look at this thing. The ml, H is equal to ml. This very type of H is called latent heat. Why this very type of H? This first thing is called specific heat. Because this one is causing a change in temperature. A change in temperature. But this one, there is no change in temperature. So this 2H is for specific heat. While this last H is for latent heat. No change in temperature, there is change in temperature. So when ice block is converted to water at that same 0 degrees temperature, which of the formula are we going to use? Is it these two or this? The answer is what? This. And we will not specifically add F because it's being converted from what? Solid to liquid. So we say mass times latent heat of fusion. Fusion. I hope that is clear. Good. Now we move on from there. After it's now water at 0 degrees Celsius, further heat that you add on it will now cause the water is why I use this. Now when the water is now at 100 degrees Celsius, it wants to be converted to steam at that same 100 degrees Celsius. Because during change of state, there is no change in temperature. So what heat will you make use of? Latent heat formula. So it's latent heat formula that will be used up here. So ice block at 0 degrees Celsius, finally to steam at 100 degrees Celsius. These are the different heats that was used up. So the total heat will be given by ml subscript f plus mc times theta theta plus ml subscript v. When you impute the values given for mc, theta theta, lf, lv, the final answer you get using this will be the total quantity of heat. And this is known as heat summation. I hope that is clear. Now we know that, moving on to something else called Joules equivalent. Joules equivalent, also called mechanical heat equivalent. This is talking about, sometimes you notice that when work is being done, some energies tend to be what? Lost. Let's say due to friction, let's say due to air resistance and the likes. Now those energies that are lost, is it that they just disappear? Those energies, is it that they just cease to exist? Remember, we said that in nature, there is conservation of mass and there is conservation of energy. So there's nothing like energy lost to thin air. It just disappear. There's nothing like mass we just lost or matter will just disappear. Okay? It's not possible. So when work is being done, some energy that is lost, where are they actually lost to? Did they just disappear? That's what brought about Joules equivalent. He's stating that the energy that is being lost is converted to heat. So whenever there's an energy loss, the result of that energy that was lost is heat. So if 12 joule of energy was lost, that 12 joule has been converted to what? Heat. Okay? And that's what makes your body warm during cold weather. Okay? And that's what makes the parts of machines, okay, to wear out. Is because of heat. And this is the relation. Energy loss is equals to heat gain. So as energy is being lost, heat is being gained. I hope that is clear. Sometimes you might be asked to find the energy loss in calorie. So after you have gotten your answer in joule, this is a conversion factor. 1 calorie is equals to approximately 4.2 joule. 1 kilocalorie, in case you were asked to find your answer in kilocalorie, is equals to 4,200 joule. So take note of these two conversion factors. And that's all about for Joules equivalent. Lastly, we'll be looking at the big deal here, which is called the principle of calorimetry. This is the principle that governs everything we have been saying ever since. And what does it state? Heat loss is equals to heat gain. Let me explain. They said this applies to what? Mixtures, cooling process, and heating due to electrical energy. Now let's analyze something. The first one is called mixture. Now imagine you are in a cold environment and you want to take your bath. Let's say you get your water from outside, from the rain source. Let's say that water was at 10 degrees Celsius. Normally you won't want to use it to take your bath because it's very cold, is it not? You won't want to use it. So you now decide to boil a separate water. That water that you boiled, by the time you're bringing it to go and mix with the other water that you got from outside the rain, the hot water was now at 80 degrees Celsius, but the cold water in the bucket is at 10 degrees Celsius. Now by the time you mix it up, what you are doing is you are actually applying the principle of calorimetry. Now what do you observe? Cold water at 10 degrees Celsius, hot water at 80 degrees Celsius. Now, once those two waters start mixing up, do you know that some heat will be gained from the hot water at 80 to the cold water? So heat will be gained from the hot water to the cold water, okay, such that the temperature of the hot water will start decreasing, while that of the cold water will start what? Increasing. Okay, they will reach a balance. So imagine from 80 is decreasing, while from 10 is increasing. So they will reach a balanced temperature, let's say 40 degrees Celsius. By the time you now put your hand, like, okay, this one is okay for me to take my bath. What you just apply is the principle of calorimetry, that whenever there's an heat loss, there will always be a heat gain. Now, a second scenario this applies to is called the cooling process. Now, when your body is hot, let's say you have exercised, you run a race, and and your body is hot, would you naturally prefer to be in a cold environment or a hot environment? The answer is a cold environment. Do you know why? Whenever you're in a colder environment than your body's temperature, you tend to lose heat to the environment. So you will be losing heat, the environment will be gaining heat. And that is what the principle of calorimetry. Is it not? Good. And lastly, we have what they call heating due to electrical energy. Now, a typical example of this is your boiling ring, the one you use to boil your water, that electrical device. Now, once you start heating up the electrical appliances by connecting it to a power source or a power supply, you notice that the heat that is being generated, first of all, the electricity that is coming in from the power supply is being converted to heat in the coil of the boiling ring, and that will now be converted and used to what? Heat up the water. The electricity that is coming from the power source, because of the resistance in the coil, it will be converted to heat, and that heat is now what will now heat up the water. So all of these are due to application of the principle of calorimetry. So guys, this is the background knowledge you need to have for your calorimetry calculations question. Once you know all this and the formulas too, trust me, you are good to go. So in subsequent classes, I'll be solving questions under calorimetry to show you how all of this work. Thanks for watching my video. I hope you enjoyed the class. Thanks for watching. See you guys in my next video.